Okay, so essentially I'm talking about a couple new ideas that I had. The first one is this intuitive idea that we have that consciousness is continuous, which basically is not true. It's discrete. You could say that it's constantly in the past because we're processing information, and that takes a certain amount of time, and therefore the result of that, which we experience as consciousness, is a little bit too late. So you could say it's from the past. But then you could say that intuition forces a dichotomy because intuition is this kind of prescience for the future. And so I thought about that for a little while, and I had thought about this idea I had a while ago, which was that our minds are kind of like multiverse approximators because we're able to bend the laws of physics, so we're able to extend them, shrink them, whatever. It's kind of like a multiverse generator. And then we're also Gödelian generators, I call them, because even if you were to be able to experience the infinitude of multiverse and every single law of physics in all of them, we could generate a new law just from the fact that we were able to experience all those other, and then in some recombination of our automatic intuition, we'd be able to create new ones. So the basis of how I kind of developed ideas from thinking about this for a little while was thinking about Feynman diagrams. So a Feynman diagram, this is the simplest version in quantum electrodynamics, which is the area that's most well understood. It's actually just these 6 diagrams here. That makes up pretty much all of quantum electrodynamics. It's just the amount of combinations, rules for how you can put them together, and everything that can basically explain pretty much every phenomenon that you know in regular matter once you combine it with the electroweak force. The fact that it's not connected to quantum chromodynamics, QCD, doesn't necessarily mean that you don't understand the interactions, because pretty much all of chemistry is just QED, but it does mean that we don't understand everything. But so this one, for example, is an electron. This is the electron going forward in time, that's why it's an electron, giving off a photon, and that changed its angular momentum. So it's still going forward in time, but it changed direction in space. That's just representative of angular momentum. This is a positron because you always go this way because this is the direction of time, but it's going backwards. So that's how you know it's a positron, and it gives off a photon, and that makes it change angular momentum as well. This is actually an electron and a positron, and they're annihilating, creating a photon. This is an electron and a photon. It's absorbing the photon and therefore changing angular momentum, but that also means that it increases in energy. This is a photon. Let me see. They produced a positron and an electron. It's called pair production. And this one is a positron that absorbed a photon and then gained energy and changed angular momentum. So those are the 6 basic Feynman diagrams from QED. And so I had this idea that if these are describing the interactions in your brain and you're processing in discrete moments, then actually you could be in, like, let's say one of these units of time. You're right here, and it processed some of those Feynman diagrams from before, but your consciousness is here, so it could process some after. And depending on how you slide these bits of time that you have here, you could be getting information from a positron or an electron in imaginary time. So therefore the information you're getting could be a computation that's literally from the future or from the past. That was kind of the idea, the original idea. It's kind of strange, and I wanted to understand it more. So I had these intuitive representations for Feynman diagrams and just a basic Cartesian coordinate system. So you have one of these Feynman diagrams, and then you can flip it across the Cartesian. And so you could say space and time. You can label it any way as long as you're consistent. So this could be time, this could be time, this could be time, this could be time. as long as you choose one, if this is time, then this one has to be negative time. This has to be space, this has to be negative space, or you could flip those actually. But if you choose this to be time, this has to be negative time, one of these has to be space, and one of these has to be negative space. And so because of that, you get this strange idea, which doesn't exist in the original Feynman diagram, which is negative space. So Feynman had this very deep understanding about how antiparticles are kind of time reversed, but I don't think he really thought about space reversibility because of the whole space-time equivalence. They just kind of took it for granted. But I just gave this as an example of one going in the other 90 degrees axis and at a different angle, but you can mess with these to develop the 6 fundamental Feynman diagrams for QED, and you can do it based off of these symmetries. But then I thought that's superfluous because you're going to have 8 here, you really only need 6. So I was thinking, well, you can represent them on a triangular grid. So that's where I had this kind of tetrahedral shape where you have these kinds of directions of space, 3 of them actually, instead of 1, and then this one direction of time. And then I thought, well, you could have the tetrahedron and one below it, and then you could have a negative direction of time. And so then that gives you all of the symmetries of the 6 Feynman diagrams in a kind of strange non-Euclidean space that's kind of tetrahedral in nature. And that's important because all the platonic solids can be made out of tetrahedrons, except I think there's one that's pyramidal that you can't make out of tetrahedrons. But this is, for example, an icosahedron. I just kind of made a surface perspective of the lattice based off of tetrahedron, and it goes off of the 60-degree angle rule for kissing numbers for packing spheres and dimensions. And so I was trying to develop, but I haven't learned enough math yet for how to do like basic basis vector, determinant, coordinate transformations, all that stuff, eigen vectors and values for modifying coordinate system like these, which are representative of a certain set of Feynman diagrams, because then that would allow me to understand the best way to represent these transformations, these symmetrical transformations, so that I can just make it as simple as possible in terms of understanding how to represent them using that system of space. And so that 1, 2, 3 by the space and time for any one of these arrows that you can arbitrarily designate, it basically just means like that you can have up to 3 dimensions in just the regular Cartesian system of space or time. So that's kind of arbitrary because really it's renormalized as space-time once you consider the quantum field interpretation of relativistic calculations for quantum mechanical systems. So the point of this was obviously, like we were thinking before about hyperchirality and subplank spaces, like this virtual black hole, white hole particle field that exists in subplank space, but it's causally separated. You could think of the electrons as black holes, so they're convergent and convergent in time, and the positrons as white holes, they're divergent in time, basically. And I just give them a subnotation of subplank just to explain that they're subplank or extremal white holes and black holes. And so you get this kind of understanding that you can explain this very difficult idea to understand for most, I think, of Planckian frequency bounds, which is that the universe has a Planckian bound, a lower bound in causality, and that comes naturally out of quantum mechanics, and an upper bound, which is some kind of event horizon surrounding either the light sphere from all the possible local regions, you could say, from your entanglement reference frame. But really the true Planckian upper bound is like the black hole surrounding our universe. And there's like, it's fractal, so it kind of like is, it repeats infinitely, so it's not like really, it's really only an objective measure when you have an entanglement reference frame. But anyways, so the idea of consciousness also having a Planckian frequency bound, which from sound is already understood as that experiment where you can chop audio into 50 millisecond bits and then mess anything up in between one of these bits, as long as you keep them in order, and when you listen back to that audio, you'll still be able to make sense of it. And that's because your brain decomposes the frequencies of the audio into their components using your brain basically does natural Fourier analysis on the audio, and therefore you're able to extract the meaning without it, without any, the changes in order don't perturbate the general average of that. So basically you don't process meaning when it's given to you in bits of audio in less than 50 milliseconds. You do at least 50 milliseconds or more. And there's probably some upper bound on that, in which you would also stop processing the meaning, but I don't think that's been as experimentally shown. And so basically from that, you get this idea that I had, which was that entropy doesn't make any sense without Planckian bounds of any kind, because entropy is just basically how disordered information is. It's actually a relative measure of complexity. So, like I was saying in high school, I had this idea of the fractal wave, which is just like you have a wave, and then there's a point on that wave, and that point can be decomposed into something that contains a further wave that has a point, and then you just kind of repeat over and over. So it's like an infinite Fourier, because you can imagine that instead of it just decomposing into its component sine and cosine waves, that every single wave has a point that is complex. So therefore it's a complexity fractal wave. But anyways, complexity through quantum circuits, through Susskind's paper, are known to be linear, essentially. That's kind of wrong. Linear, and then constant, and then exponentially decay, and then linear again, and constant, exponentially decay. But that's actually for a closed system. You can actually kind of just describe it as if there was just one black hole with some projective space inside. But because it's fractal, they probably didn't think about it this way, but it appears like the entropy dips at this point because of the whole CCC interpretation, actually at this point, because of the whole CCC interpretation from Penrose, but actually it uses this as a basis for increased complexity. So the whole point of the universe of the multiverse is basically McKenna's novelty interpretation of time, for the sake of increasing complexity. And the internal projective space of the black hole is, like I was saying, is the automata. Light is the automata. The black hole is the generator of automatas, and the white hole is like a time-reversed generator of automatas. Sounds a bit tough, but basically you can think of the automata as a set of rules in some amount of dimensions of time and space, or whatever gauge symmetries describing some kind of rules for all of this mess of quantum mechanical, basically quantum gravity, because that would be the ultimate description of the unification of this with QCD and gravity. There's just some set of rules, essentially, and that defines the complexity. And so if those rules are embedded in a space, like in CCC, where it all averages out for enough time, then it'll act, it'll perturbate. Basically there'll be fluctuations in that energy density, and that just happens in the same reason that in an empty vacuum of space there's virtual particles, essentially. And then there will be a symmetry break. So this just represents a tendency towards symmetry, and there's a symmetry break, and then it linearly increases complexity until there's a symmetry again, and there's a symmetry break, and it just does it again and again. Don't exactly know what causes the symmetry breaks. The current interpretation is this idea that entropy in a system just drops over time when it acts quantum mechanical in nature, and that's just something that's natural for quantum mechanics, and then it'll increase, which is essentially proportional to complexity increasing linearly. Except entropy is strange because the interpretation of it is that it would just keep increasing and increasing until the black hole evaporates or explodes, which is kind of one of these points, like here. But it's not exactly clear if that's true or not. That's kind of a really deep question. But the reason that's so tough to understand is because of this thing called the electroweak phase transition. So you can think of regular matter. This is just a phase transition graph for regular matter. There's gases, liquids, and solids. This is a critical temperature for liquids where they can be compressible. A critical temperature for gases where they turn into vapors. A critical pressure, this is pressure and this is temperature, for solids. And let's see. This is kind of like, I think it's called a triple point, and this is another critical temperature and pressure, where any kind of liquid would become a gas again. So that's pretty commonly known, and then a plasma is less commonly understood, because the strange thing is about plasmas is they can exist on a wider scale of temperatures than what would seem normal. They're really just very highly ionized systems. They're not necessarily solid, liquid, or gas. And so we know that in the early universe, there pretty much was only plasma, and right now you can pretty much describe the universe as only plasma. There's this other graph to the right here, which is just talking about free Gibbs energy and Higgs field, like the energy in terms of gigaelectron volts for both, except energy kind of can be taken from different perspectives, so this one is kind of taken from the perspective of temperature. And there's around 100 gigaelectron volts where this electroweak phase transition occurs, and so that's kind of this idea of like a triple point, but for the forces instead of the states of matter. So basically the idea I had was that the prefrontal cortex has these pyramidal cells, and these pyramidal cells are kind of like these tetrahedron over here that seem to have this kind of, like you can imagine the axon coming out from there, directionality and time, which is actually just dependent on an entanglement reference frame, which is an interpretation of exactly what interaction is creating what information and where it's coming from in time. Because your consciousness is discrete for this reason, you have the illusion that you exist in the present, but the present is just an average of information that you're getting from the past and the future, essentially. Aside from the fact that we're processing information and then the conscious moment is after that, therefore this information is necessarily from the past, gives this illusion that we're constantly going towards a future, because the information we're getting precedes us, and yet we use this to constantly predict, and it's a self-referential programming. So basically you reference the state that you were in, and you use that to reprogram yourself for complex motion in the future. And essentially, since we originally had any kind of ability for exploration, that was the basis of extrovert intuition, which is a primordial Jungian function. So that was the beginning of not a language, but some kind of self-referential system. As soon as we had introverted intuition, we already had bilateral symmetry in that complex motion, or that system of complex motion. But I didn't erase this because it's actually really important from that original drawing. It's very strange, but this entanglement entropy idea is critical to understanding what antimatter is. Because you can imagine that whatever information is being projected into the black hole has to preserve some kind of symmetry. And so there's this woman named Emmy Noether. She created the idea of Noether's theorem, which is a preservation of information, or the conservation of energy in any system. So pretty much any conservation law you know is a result of her ideas. And it was important because when Einstein created relativity, there was some problems with the conservation of energy, specifically in a there's like whenever you create a coordinate transformation, which is kind of the basis of the cosmological constant and expanding space, contracting space. She basically from this sprung the idea of gauge fields, which is the general idea that there are underlying symmetry groups for particles. But the reason this is important for understanding what antimatter is because of the ER equals EPR idea, which, if you remember, states that there's basically no difference between entangled black holes having a wormhole between them and entangled particles. And so this idea of an entangled particle essentially means, in the way I understood it, as invariantly time-symmetric within a Planckian bound. So essentially that means that there is this kind of similarity to the idea of electrons and positrons, or black holes and white holes being time-symmetric, and any other particles being time-symmetric, which we measure as properties of opposite spin. So this one will be up, this one will be down, this one will be up, this one will be down, which spin, as explained before, is essentially this idea of hyperchirality, and the fact that when you measure a system of hyperchirality, it gives the perception of chirality, which is essentially meaning. Remember I was explaining before the whole yin-yang plasma idea, like if you had this kind of liquid that was constantly converging, and this other liquid, or you could say just plasma, that's diverging, and then you were mixing it, it would constantly be evolving in a very strange way, and you can kind of describe that as some kind of strange automata. But you can't have synthesis without thesis and antithesis, essentially. And you can't have present without past and future. And you can't have chirality without a hyperchirality. There's this kind of idea that triality, from triality, you will always get a dichotomy, which is chiral. And so chirality is kind of the real part. The synthesis part is the part that isn't really, I would say, real. It's like consciousness, thinking that we exist in the present all the time. It's really something that was created. It's a kind of consistency mechanism for a cohomology. So it's like that one Penrose triangle that I talked about a few times. It's completely impossible, but we rationalize it, we create some kind of consistency rule for it to allow it to connect, you could say, to whatever understanding system, imagination, rationality, whatever, that we have for in whatever our right hemisphere is doing to do that, understanding our world. So basically we're constantly doing this for the sake of preserving consistencies of cohomologies in the hyperchirality of in general whatever cognitive function is performing. So all of this, I think, in my idea of it, is being coordinated by the prefrontal cortex, which has most of these pyramidal cells, and they mostly connect to the thalamus, but they also connect to different regions of the brain. And it seems to me that it's coordinating. It has this really important function in terms of planning and this self-referential state of awareness that I think it's essentially creating the present for us. It's creating a consistency system for these different spaces, interpreting the language and saying this is the actual result of the cohomology. This is what the Penrose triangle actually is, when it's actually impossible for it to do that. So it's taking some average. So this actually, it has a lot to do with understanding Einstein's relativity and the interpretation of simultaneity as subjective, based off of your reference frame, and the idea of locality, which is just the idea that information can't travel faster than the speed of light, unless there's a wormhole connecting it, and in that case, it's still traveling at the speed of light. It just because of certain rules in imaginary time, it essentially had less space and therefore more time to perform that action, and therefore did not break the rules of locality. And then one last thing, the consciousness has a multiverse approximator. If you go back to the complex function dynamical system interpretation of a chaotic variation in rules, depending on how you change on this coordinate grid, like you can go divergent to convergent, and on the edge is like the dance between order and chaos that Peterson talks about with McGilchrist. There's this is from the previous board as well. There's like a small difference creates a huge change in the amount of rules and game trees, which you can imagine as describing some kind of state evolution of an automata, and they follow these kinds of symmetrical rules, Fibonacci spirals, etc. The important part about all this is that in physics, when you understand the Lorentz force as it relates to the simultaneity, locality rules for relativity, you get this principle of least action, which I think is the kind of key to understanding this. If you go back to the Feynman diagrams, the way he actually calculates one of these interactions is he has these algorithms that tell you which ones actually matter, because there's a virtual, when you connect these in complicated ways, these can all happen in different combinations at the same time. And so there's, he uses really complicated integral path formulas for algorithms that tell you these are the paths that matter the most, that contribute the most, like a statistical average. Basically saying, well, with these data samples, you'll capture 95% of the population average or something like that. And therefore, you, those are based off of these things called probability amplitudes, which basically tell you that there's like negative probabilities for particles to take certain paths and positive probabilities. And the way I think of those is that they're essentially part of this chiral mirror perspective, or the entangled particle perspective, which is that the negative probability amplitudes are actually positive, and in the antichiral space, or the time symmetric space. So the positron would actually argue that their perspective is the positive probability amplitude, and the electron is the negative. So that's why I had the variability in the labels for the for these directions, because you can have you can make it arbitrary in which direction you want time to be going or space to be going. I just think because of preserving symmetries, the tetrahedral coordinate system would allow you to describe the state more simply. Essentially, that is the path of least action interpretation, which is why I was talking about this. And so consciousness, that's where I finally put this all together. Consciousness is always a path of least action. It doesn't mean that when you want to walk across the room, you're always going to take the shortest path. It means that your consciousness is some kind of discrete operation that is taking an average of an antichiral set of computations, dual antichiral set of computations, which give you an average, which you interpret as the present, and each of those will always be an average that is a least action principal average, because that's necessary energy conservation, information conservation. Really, it's all of this is about complexity. So it's a complexity conservation, and that's why I think of it as a constant open system. It's a complexity conservation that follows Emmy Noether's theorem. And so I kind of went through it quickly just because I knew this video would be pretty long. And then we can talk about it later in detail. But that's where I'm at, and I think the biggest issue with this is the fact that the hypersphere interpretation, which I think naturally arises from kind of a higher dimensional Wick rotation interpretation of these coordinate transformations of Feynman diagrams and different coordinate systems that represent the paths of least action more easily. That basically you can get the symmetries quicker out of the whatever invariant time symmetries you have in that space. That whole thing is not understood for quantum chromodynamics. The electroweak system, though, I sent you a couple papers on that. Seemed like since the late 90s they've had some pretty good understanding. Now they have these things called loops, which when you connect these in complicated ways, they loop together in weird ways, essentially. And computationally, I think they've got into like 4 loops, and basically instead of electron positron, they'd be like quarks, and then these would be gluons or whatever. They've gotten to like 4 loops. They're trying to get to like 5 loops, I think. But the point is that they can calculate these and get a path of least action in a simple system, but you can imagine this is a single electron and positron and photon. Even just a fraction of a part of a piece of DNA has millions, if not billions, of these. And so the complexity already is insane. The fact that it scales to this idea of a pyramidal cell, I think, is some kind of insane level of symmetry that should be rare. And I also was why I freaked out one time and I was like, pyramids, because I kind of connected it in my head. But yeah, quantum chromodynamics understood. The way I think about gravity is like plasma, essentially, that it doesn't really match these other phase states, which you can think of as the weak, strong, and electromagnetic forces. It kind of pretends to be all of them. That's how I think of plasma. It can be all of them as long as they're ionized, whereas ionized in this case doesn't mean that it has these gauge particles, or like the photon or the gluon or whatever. But in terms of, in general for gravity, it means it has some kind of unified version, which is called the graviton. And so that's why I was thinking of these in terms of black holes and white holes. So you can think of like, this is a black hole that gives off a graviton and stays a graviton. This is a white hole that gives off a graviton and stays a white hole. This is a black hole and a white hole that collide and give off a graviton. This is a black hole and a graviton, where it absorbs it and gains energy. This is a photon that pair produces a black hole and a white hole, and this is one where a graviton and in a white hole creates a higher momentum, higher energy white hole. And so that's why I was thinking of diffraction patterns of white holes and black holes. Like you can think of them inside of a black hole, kind of like a diffraction pattern of these, and that's ADS space, anti de Sitter space. It's a different kind of perspective on it, I think. But the only version of these where you start off time without a black hole or a white hole is this one, called pair production. So that tells me that gravitational waves are kind of like the origin of black holes and white holes. But in order for you to develop a gravitational wave, you need any kind of strong gravitational force, at least in terms of your reference frame, and maybe in a smaller fractal reference frame in the whole fractal wave interpretation. You can have anything happen and create a huge gravitational wave in a smaller fractal dimension, a subplanck dimension. Maybe, not too sure, because they're supposedly causally separated, but that's where I'm at with it. I think that the metaphysical Gödelian generator multiverse approximator is an indismissible idea that essentially shows that our brains are necessary in the metaphysical evolution of the world of automata. I'm not entirely sure that relationship exactly. I think it has to do with the speed of causality, being an inherent property of a space, like that one video that I had shown you, that the speed of light's not really about the speed of light, it's about the speed of causality. I'm not entirely sure if just being able to imagine faster or slower speeds of causality is what allows them to exist. I don't really think of it that way right now, but I do think that there's an ignorable principle here, which I think of as, we were talking before, as dream time, which is this kind of higher level above imaginary time, in which you can just collect this, because as I was saying before, remember with the music of the photons, of the twisters that make up the photons past the firewall that are hitting the event horizon, that they take an infinite amount of time to do so. So those must be generating these gravitational waves that create the black hole white hole diffraction patterns inside the black hole, which each one is kind of like its own universe or whatever. The point is that the sum of that, until this black hole evaporates and explodes or whatever it actually does, the sum of that is not an imaginary instant, but an imaginary set of time, and the sum of all of those across many scales, which in a virtual black hole white hole field, which is sub-Planck, could essentially mean the same thing as this idea of when you get a lot of these together, there's all the possible combinations happens, but we only see one. So too, basically everywhere in space, there could be these virtual black hole and white hole fields, essentially at every scale, everywhere, that we wouldn't experience because we're part of a single set of imaginary time, just like a diffraction pattern of light and electrons. You only see one result of it. You only see one result of those because we're within one imaginary instant. But there's a set of imaginary time that would actually be the same thing as describing when one of these interactions, when you connect these in weird ways, and they say, well, all the possible ones happens, but we only have to look at the important ones. An imaginary time is essentially saying, look at all of them. They all happened within this imaginary time. And that's why it's this symmetry preserving system that basically does all the possible combinations or whatever, as I was talking before, which is basically represented by this state of quantum bits or whatever, and the whole Seskin circuit idea. And so I call that sum of all possible imaginary times, which is an imaginary time is the sum of many imaginary instants, in which we live inside an imaginary instant, but I call all those sets of imaginary times dream time, the infinite sum of them. And that infinite sum of imaginary time called dream time seems to me very similar to this idea of a Gödelian generator, or this idea of introverted and extroverted intuition and conscious loops, which we call consciousness, or dreaming, essentially. And so that's the insanity that I was talking about.